In the first part of this lecture, we implemented the Transformer encoder, which consists of a self-attention block here, and then uses a feed-forward network to encode tokens that you would send in. In the second part of the lecture, we want to build the decoder and actually train a name generator that will generate random names that are a lot better than those that would be generated with a bigram model. We already have the multi-head attention part, we already have the feed-forward part. What we don't have is the masked multi-head attention. So the idea here is that this thing here would generate a random name that comes out here at the end. And the way it does this in a batch is to provide some random inputs and clock out a new prediction, and then take this prediction and add it to the output, so it says here shifted right in the original paper. And so in our case, what we want to do is we want to seed this with the space character and then predict the first character that the name starts with. Then we seed it again with the space and that character we get the second character and the third character and so on. Now the problem with self-attention would be that it would look at all of the characters at once, and when we want to train this with a complete word, and a complete word should predict the target distribution, then you would have something that would also look into the future with self-attention. Now we want to do it in a way that allows characters only to look backwards, and this is where the word mask comes in. So this is easiest to understood by implementing it in Python. And what we do is we start with our encoding that we have and grab the shape. So this was the number of batches, the tokens, and the number of classes. And then we print out how the unmasked attention would look like. And so for that, we just grab the encoding and we multiply it with itself. And this is something we've done at the very beginning of the first lecture. And now we run this through the softmax layer to turn this into probabilities. I think this should be it. Looks happy. And so what you see here is something like that. And here, what we started with today, this is the encoding of Leica. The first character with the first character has the highest probability. Here you see the diagonal has the highest probability, but then you will see that the A is actually happening twice. So here you have the A and you have the A here at the end. So if you don't follow this, please watch the first video, the first part of this lecture first. Then this will make a lot more sense. Now what we want to talk about is the masked attention. And the way to think about this is to use the built-in triangular matrix generator from Torch. And we can do this by feeding it with 5x5 matrix in this case, and turning this into a lower triangular matrix. So you see here, the lower triangular matrix is 1 in the lower triangular part and 0 in the upper one. We can also turn this into a binary mask. So we have true here where it was 0, and we have false where it was 1. And this way we can use this in the Torch masked fill feature. So let's create some additional data structure here where we take this attention, self-attention matrix, and now we want to use some masked fill to set all of the elements where this is true to -infinity. And why we do this will become clear very soon. And it's already suggesting this here. Once I run this through a softmax to turn it into probabilities, I want to have the values to be actually 0. So softmax uses the e to the power, the exponential function, and when you had if you had a 0 here, then e to the power 0 would be 1, which is what we don't want. We want this to actually be 0, so that these tokens will be ignored. So here the first character will only look at the first character, will not look at the ones that follow. The second one can look back, the third one can look back too, and so on. So let's update y here to be like this, and then do the softmax at the end and print the whole thing. And now we have masked self-attention, and now the first character is only self-similar to the first. We completely ignore the relationship of the first character to those that follow. Now, if we want to change the self-attention block to be the masked multi-head attention block, we have to actually just add these lines, and for that we copy and paste our multi-head attention block, which we have here. We copy this, and we will call this masked multi-head attention. While I'm at it, I can do this here. And now this all looks pretty good. This is the first step where we want to have the weights. And here I can update them using this equation and call this attention weights equals attention weights. And so this should be it. We have the softmax already implemented. All what we've done is we have really just suppressed that upper triangular matrix, and I don't know a better way to do that than really just copying and pasting the whole thing and just calling it masked multi-head attention. And now I can put my transformer encoders or decoders together as I want, using the different classes. With this, we are ready to build our Transformer Decoder layer. So we're going to build this entire thing here. In this case, I really want to only decode names. So I don't need that cross-attention piece. And so what we will do is we will take our new masked multi-head attention and we will put a feed-forward layer in front of it. And then we're gonna run this entire thing x times through, or n times, sorry, to stack these decoder blocks up. So let's implement this. We have everything we need, and we create a new class, which is the Transformer Decoder layer. We have to initialize everything. We want our model dimensions, the number of heads, the feed-forward network dimensions, and the dropout. First thing we do is we call the superclass init function. Then we initialize our self-attention module using the masked multi-head attention module, and we pass on the D-model and N-head parameters. We now have our feed-forward layer, and we could copy and paste this from up there, and we use again a sequential neural network architecture, and we start with a linear layer, and it already wants to do this, so we blow it up to this dimension of the feed-forward, 2048 by default. We run to a rectangular linear unit, and then we bring it back to the model, and we have to close this parenthesis here. Then we have our layer norm. And we do that twice. And we have the dropout layer at the end. All right, so now we can implement the forward method. And the first thing is we start with self-attention. That's right. Then we add the layer norm and the residual connection. Ooh la la. This is a little much that it invented here. And by the way, this is a transformer that is a transformer decoder that is actually suggesting all of this output here all the time. So this is pretty much what we are building right now, which is interesting and maybe ironic. Now we have the feed forward layer, and we provide our input source to it. And we finish everything with a second layer norm here. And here we add the dropout. So that's already it. It understands what I want to do. And we can test this. Very good, and see if it works. So we forgot to provide something. And I have some inconsistency here. And we are missing the parentheses here. So many problems. Attention. And there we are. So we have just put these things together just the way we've done it before with a couple of typos. Now everything should work. And we are able to run our encoding of Leica through this decoder layer. So now we have all the components to actually create a random name generator, which is the decoder layer that we just used here, plus this linear layer and the softmax at the end. And we can then feed the positional encoding in and an output embedding, and we should be able to generate names this way. All right, so let's call this a random name generator. There it is. And we inherit from the neural network module. We in our init and head and layers and the maximum length that we want our words to be. We call the superclass. We copy all the variables over. And now we do one thing. We have been using one-hot encoding so far, and we could do this, but we can also just use a trainable embedding. And in this case, or trainable encoding, we will just use an embedding from Torch. So in this case, we use the embedding implementation. And what we want is something that takes the length of the alphabet. So we take the embedding, we have 28 rows, and then we want to project this down to the dimensionality of the model. And this is something we can choose, and the bigger that dimensionality is, the more we can learn. So that's something we can play with. Now we can use the positional encoding that we defined earlier. But we can also go and use a trainable embedding, and in this case we would use WPE, and in this case we use also the embedding, and we use the maximum length of our word or our names that we want to generate, and the dimensionality of our model. So finally we implement the decoder, and we can do this as a list. And so here we use list comprehension, and it actually wants to do the right thing. So this is the Transformer Decoder layer with the dimensionality of our model, the number of heads, and we want to do this as many times as we do have layers. So this is this parameter here. So if you have one layer, it will add one of these blocks. If you have 20 layers, it will add 20. And we can then add the linear layer and the softmax. So it takes the dimensionality of our model, which can be anything, and then projects it back to the 28 characters that we have. And finally, the softmax layer that we can add to the very end is also implemented by Torch, and we always go over the rows. So with that we can implement our forward function, and here we need our parameters. So we get the number of batches and the number of tokens. Now we do the first step, we embed using our embedding that we defined here. So this is this step here. We are taking our input and embed it. So we skip this one hot encoding, but we actually add some opportunity to learn something here as well. We then generate a positional encoding, and we always just generate numbers from 0 to the number of tokens that we want to generate. And we have to always provide the D-type, otherwise these things won't be added together. And here we add the batch dimension. And now we can take our embedding and add the positional embedding to it. And so the positional embedding is a learned embedding. It's just a matrix, and we can look up items from it or rows from it by providing the positional encoding. So in this case, these are numbers from 0 to t, and it will add them to our encoding. So now we have to run all of our data through the decoder layer. So I just run it through it layer by layer. Already did this earlier because it can tell what I want to do from our definition up here. And now we run this through the linear layer. And finally, we run it through the softmax layer. And then we can return it. So now what we need to do in order to generate names, we need another function which we want to call generate. And this is inference. So we tell Torch that what happens from now on shouldn't be using gradient computations. And we can now implement a function generate, and we provide a token to start with and the maximum number of new tokens that we want to generate to limit the length of the names that we get. And so I'm looping through this max new tokens. And the first thing I do is I actually take my token and run it through the forward method. So this gives me a bunch of logits, and in this case it's actually probabilities already, because I do have a softmax here. I now drop all of the tokens in the beginning and just look at the last one. And the reason for this is because all of my tokens encode the same information, so I need only what I would call the class token here, and use that probability distribution to generate the next one. So in this case I have softmax twice because I have it here already, so I actually don't really need this. These are already props in this case, so I can just call this props are the logits. And now I can draw from this distribution by using the multinomial distribution. Now, if this next token is happening to be the space character, then I want to break. So this is the space character, and then I break, and otherwise I concatenate it to the tokens that I have and return it. But here I actually want to seed it with the space. So the first character of my sequence is always the space, and I want to drop that. So in this case I return all the batches, but I drop here the first character and then only provide whatever was generated after the seed. So I think we can try this. Let's do some manual seed to be consistent and instantiate it. Now I choose an embedding dimension of 32. I have 4 heads, 2 layers, and then I want to get names up to 16 in length. And I send all of this model to the same device that everything else lives in. So let's see if that works. Here's a init function is not correctly initialized. Alright, so this worked. Now I can see if I get anything from this. And for that I need to call my generate function, and I have to seed it with something which is the space character in the beginning. I have to add the batch dimension. I have to put this all onto the device, and I want to generate up to 8 characters for starters, and then I have to decode all of this and turn this into a list, and then I can take the first batch from it because I generated batches inside. And I need to, actually this guy comes here. Does this work? Yes. So I probably have done something wrong here with the ordering. This is the tensor, so I have to unsqueeze it here and then X here, and let's test. All right, so we have our first random name. And of course, this is completely random because the model hasn't been trained. So you see it even has these dots in here, which we should never see because they should only be in the targets. All right, let's get 10 names so we can later test this once we trained it. And we need to put this into a print statement. All right, so we have now a way to generate names. This is all batched, and this should all work wonderfully with our optimizer. There's one more thing we can do. We can actually print the model size here, and we can add this here. And so let's print the model parameters, and we do a sum over all of the numbers of parameters inside all of the parameters. And I think that's it. Something wrong? Yes. So this is a function, and I have 277,084 model parameters in this model that I created. So we can play with this a little bit and see what happens if I reduce the dimensions. So you see then the number goes down. I can even go down to, well, this doesn't work. I cannot have less than heads. So this should work. This is the minimum I can have. You see now we have only 37,000. And we can go and have 28, which we originally done, but I actually chose 32 here, so you see that this number is completely arbitrary. All right, let's see if this still works. Yes, it does, and now we can do training around it. So I have already prepared the optimization code. We have done this many times now, and what I'm going to do is I use the atom with weighted decay. I provide the model parameters. I have a learning rate, I have weight decay, and I have some other parameters here for this atom W optimizer. We are training this for 10 epochs, and what I do is I go and get a batch from the train loader. So one epoch is going to go through the entire training set once. So there are two follow-ups here. I have my optimizer zeroed, and then I use my model to predict the logits. I then get my targets and compute the cross entropy loss. As before, I had to turn the batches, or actually reduce or remove the batch dimension by stacking these things all up before I provide them to my loss function. I do the backward pass and then call an optimizer step. So let's run this maybe once for one epoch, and I think this runs on the CPU now. Let's see what I'm using here. Let's actually think about what happens here. When I print the loss, I actually print only the loss from the last batch. So the entire epoch is running through with many different batches, and I only look at the loss from the last batch. There's a better way of doing this, and this is to actually create an evaluate function. Let's do that here. And I want to put torch into inference mode, and now we want to use a batch size, let's say 50, and use randomly sampled batch to actually compute our loss. So we make sure we are in evaluation mode and don't compute gradients. We now create a new data loader, which is shuffling and we pass on the batch size, and num workers is 0, and the collate function is pad sequences. So this is very similar to what we've done before. We are just getting completely new data for our evaluation. Now we create a list where we want to store our losses. And now we go through our new data loader, and we are computing the losses for an entire epoch. And this should be very fast because we are doing inference, no training. We get the batches, we run the data through our model, we change the ordering to lose our batches and stack everything up. We do the same for our targets, and then compute the loss using the cross entropy function, and it already second guesses everything I want to do here. And here we actually tell the cross entropy function that we don't want to, we ignore the dots because these are in the targets only. We append those, and now I use this max batches parameter that I provided here, so we can make this a little more versatile. If this is not none, which it is here, and we are exceeding our maximum number of batches, then we are done. Now we compute the mean loss. So we get the mean after turning this into a tensor, and this is to get the number out of it. And then we turn back into training mode and return the mean loss. So this is still training. I think we have presented the data set already more than 3 times. Let's see what happens when we run inference. And what happens here is we always get the same name. And the reason for this is because something is probably wrong with the logits here. And for some reason, we should probably actually explicitly perform the softmax operation when we draw from this. Let's see what happens now. We are back to random characters because of course we trained this the wrong way. But what I also want to do now is I want to add the inference, and so I prepared this here. We can copy and paste this in. And so instead of printing the epochs, we print them together with the training loss and the validation loss. And here you see I'm using the evaluate function, and I do this after the end of my training. So this should be in there. It should be now be able to see these. Evaluate. And you see here I'm providing the validation data set while I'm using here the train data set. And the advantage of this is of course that the val data set is something that the model has never seen. So as we overfit possibly, we will get the training loss to go down, while the test loss will at some point reach a plateau. And then we see that our model size is accurate when we are entering overtraining. So what we can then do is we can make the model smaller and dial it in so that the training loss and the test loss is about the same. This is actually running for 10 epochs on the CPU before it would print out anything, because this is in the outer while loop. So let's stop this and see how this has been training. Let's fix this for the next time. So now this would print after every epoch, and I guess we have already 2 or 3 epochs in, and we still have a pretty random names. And I notice another problem. We are now running softmax here and there, and when you think about it, during training we are using the cross entropy from the forward of the model, and so the softmax that we run here is already being run in the cross entropy function. If you remember, the cross entropy function is doing softmax and then the negative loss log likelihood. So we don't want to do this twice, and this is a subtle observation here, that we want to use the softmax that is provided here only when we actually use this as a generator, but not during inference. So I also want to now run this whole thing onto the GPU, because I will forward this for you, but I don't want to wait so long. And let's get the T4 GPU, and we have to rerun a lot of the things here for this to work. Fortunately, this is all in a single cell. Our model, we can now get our training set. I don't think we need any of this, but we will need, so our test doesn't work, so I need some encoding to play with this, otherwise it will just give failures here. This is the Transformer Decoder layer. The positional encoding, if you want to try this later. The masked multi-head attention. Transformer Decoder layer. And now we can define our random name generator. See if it works. Actually is. So something here is not on the device. We can check here. Please make sure everything is on the same device. And maybe I remove this to make it a little easier for the encoding we created in the beginning with Leica was never on the device. So let's run through this. And now also the random name generator should work. And we can test it. And we get random names. Now this runs on the GPU. And we can train the model. And we should see much faster training than before. And I should actually move it to the right location so that this doesn't happen again. Much better already, and we probably can stop this already right here and see what our model gets us. And run, and we get names. And you can see these names make a lot more sense than from a bigram model. I don't think any of these are in the list. So you see Neon Day, Linan, Riven, Toner. These are all names that sound a lot more likely than what we've seen before. And we can now go on and train bigger models. We can train models on more data and then build this model that you've seen here up to GPT-2.